Cloud architecture. We've talked about infrastructure and virtualization and infrastructure as code. Let's now talk about cloud architecture. And architecture is really about how all of the pieces of a system, including people, fit together and how a system communicates among the different components of the system. There's this group called the Open Group Architecture Framework, or TOGAF, that defines some standards for what architecture is and what it means. And it has two primary definitions. The first one is a formal description of a system or a detailed plan of the system at component level to guide its implementation. And the second one is the structure of components, their interrelationships, and the principles and guidelines governing their design and evolution over time. The second definition is the one that we'll focus on in this video. Let's quickly discuss the difference between infrastructure and architecture. Infrastructure is composed of the building blocks of a system: networking, storage, virtual machines, containers, etc. Architecture is the definition of the interrelationships of those system components. For example, which protocols would the storage use to communicate to the virtual machines? Architecture tends to be a step up in abstraction from infrastructure. It's a little bit more abstract to think about architecture. We can usually define and design architecture using diagrams and text. Cloud architecture, when we talk about it, traditionally includes workload or application distribution, resources and resource pooling, how we scale in the cloud, fault tolerance and high availability, and how we build that into our cloud systems. And of course, people and teams and how they're organized to deliver business value. How all of these components work together to make the cloud what it is really cloud architecture. Let's first talk about architecting for scalability. Scalability is a big component and a big value add for the cloud. It's one of the main reasons for going to the cloud. Cloud scalability falls into two broad types. Horizontal scalability means adding or removing one or more identical IT resources and spanning your workload over those resources. Vertical scalability means adjusting the capacity of an existing IT resource. If you remember, in one of our first videos, we talked about Grace Hopper, who came up with this idea of distributed computing, and she said, in the pioneer days when an ox couldn't pull a particular cart, we wouldn't try to grow a bigger ox. We would simply add more oxen to the team that pulls the cart. Well, that's what horizontal scalability is. Vertical scalability would be attempting to grow a bigger ox. There are advantages and disadvantages to both horizontal and vertical scalability. Horizontal scaling is not limited by hardware resources. Generally speaking, I mean, there always is a limit. Nothing is infinite. But when we scale horizontally in the cloud, we can provision more and more and more containers, for example, to distribute our app across. It's much easier than vertical scaling to increase and or decrease resources. This is what AWS has traditionally called elasticity. But horizontal scaling has increased management complexity. Luckily, there are software tools out there that help us with orchestrating large amounts of horizontal scaling, like Kubernetes. There's often increased code complexity with horizontal scaling, but there's also often a decreased cost. It often costs more money to build more power into an existing, for example, virtual machine than it is to just provision another virtual machine. Because virtual machines, as well as physical machines, of course, have very well-defined limits of, for example, how many processors you can put in there, how much RAM you can put in there. Here's a little diagram of horizontal scalability, and I've mixed up Azure and AWS icons in here. I hope you'll forgive me, but suppose we have 3 employees starting out, and then we rapidly hire 3 more. Maybe we have an auto-scaling listener in the cloud that listens for whether there are more resources being requested, and then we have whatever cloud services we're using provision more virtual machines for those employees. So let's talk about vertical scaling. There are some times when you would want to scale vertically instead of horizontally. If you're not in the cloud, or if you're in a hybrid cloud situation and you're actually using physical data center space, vertical scaling might make more sense because you're really just putting more power into an existing physical machine. If you have extra processor sockets or DIMM slots for your RAM memory, you can vertically scale your machines, but only up to its physical limit. Vertical scaling uses less power consumption. We're not plugging in, or quote unquote, plugging in the cloud more machines. It's often less technically challenging, especially in a hybrid cloud situation, because you don't have to make a lot of configuration changes when you're just adding new hardware to an existing machine that's already configured. But it is, of course, bound by hardware resources. There are very much limits to how much you can shove into one machine. It tends to cost more. Here's a little diagram of vertical scaling. So what if we had the same 3 employees start and we rapidly hired 3 more employees? In the cloud, we may have the same auto-scaling listener, but we may have set it to vertical scaling. So our virtual machine just grows bigger and bigger as more employees request resources from it. In the architecture world, there's often a discussion or a debate about what is cloud native architecture and why is it different than on-premises architecture. Sometimes I see companies want to simply build the same architecture that they had on-premises in the cloud in the same way, or move an on-premises architecture into the cloud, what we would call lift and shift. And usually that's not a good idea. And hopefully after this discussion, we'll understand why. Taking advantage of cloud architecture means designing applications specifically to run in a cloud environment. Cloud environment that's elastic, scalable, disaster resistant. All the things that make the cloud super powerful, all the reasons that companies want to build in the cloud. We only take advantage of all of the superpowers of the cloud when we build our applications and workloads using cloud-native architecture. Cloud-native architecture means we are backing our workloads with disposable infrastructure. This means that a container or a virtual machine has to be able to be replaced by its same exact thing if it fails. So in the container world, and containers are a great way to build cloud-native architecture, and we'll talk about containers in another video. But we span our application over multiple containers, and if a container has a problem or blows up or something like that, we have our container orchestration tool provision an exact copy of that container to then and then replace it. We don't really fix things in the cloud. We dispose of them and then replace them with the exact same thing. In the financial world, this could be called fungibility, right? We want to compose our cloud workloads of isolated components because it's easier to fix just one small component or rebuild or replace one small component than it is an entire system. So in the old days, we used to have monolithic systems, Oracle or IBM. You'd buy your whole technology stack from just them. And then if you needed to update something, you would have some downtime because you'd often have to power down the entire machine to reboot it or something like that. But in the cloud, we're really dealing with isolated, composable, disposable infrastructure. And I know I said we generally don't fix things in the cloud, we replace them. And then I said it's easier to fix one component. But I will say sometimes we do fix things in the cloud instead of just replacing them. But it's easier to deal with individual, isolated, disposable components than it is to deal with monolithic systems. That's one of the beauties of the cloud. A great way to build on cloud-native architecture is to build on what are called containers, or this kind of newish idea of serverless, which is often really containers as a service, meaning you don't have to manage any of the infrastructure, including the containers, when you build on a serverless architecture. But here's an example of what I mean by containers, and that little symbol down there is Kubernetes. We'll hear all about Kubernetes in a future video. But containers are virtualized resources that an application or a workload needs to run. As that application or workload gets more requests for activity on it, we can have containers automatically provision more resources in a horizontal scaling way, meaning that there will be more containers provisioned as app activity goes up. We can even destroy some containers as app activity goes down because we're spanning the resources of that app over a bunch of containers. This is really a popular way to run huge apps like social media apps and things like that. They're backed by containers so that they can scale up and scale down rapidly. Let's talk about architecting for data in the cloud. I would say that scalability and data, and those two things together, are kind of the main reasons or the main advantages of the cloud. So when we architect for data, we're architecting for potentially petabytes or exabytes of data. And think about large companies that deal with extremely large amounts of data, like, of course, Amazon or Google or Facebook or anybody else really that is in the modern sort of social media or content delivery world, Netflix, things like that. The sheer size of modern data sets necessitates the hyperscalability of the cloud. The basic architecture is built on a scalable infrastructure. It's built with isolated components, and data can be streamed or batched. What I mean by streamed versus batched is probably just what you're thinking. Streaming data is live. It's coming to you as you're using it. For example, Netflix. When you're streaming something from Netflix, as you're watching the movie, those bits are coming to your Apple TV or Roku or whatever. Data that's batched is collected and then sent at a particular time interval into the system, whatever that system is. In the data engineering world, we architect for data like this. And we start with the end in mind, with the right side in mind. Those are our data analysts, our business intelligence engineers, data scientists, machine learning folks, artificial intelligence people, and any data user. We're going to get our business requirements from them. What do you need? What kind of reports, dashboards, alerts, what kind of use cases for this data are there? And then we're going to go back to all of the systems on the left that generate data for our company and think of what generates data. If it's a grocery store, anytime you scan an item that generates data, it's going to deduct something from inventory. It's going to increase something to the revenue database, right? There are lots of things we can think about. Even in an Amazon world, the source systems are when somebody purchases something, we're going to add something to a cart, deduct something from inventory. It's going to be a whole transaction. So we're going to go to our source data and figure out, okay, so our business requirements at the right side are this, this, and this, and this. And our data on the left side, our source systems, we need to figure out where that data comes from. Then we run it through this architecture of a data pipeline. This is a very generic architecture where we ingest the data, so we copy it to a specific area that's built for data analytics. We transform it because those source systems are all going to be different, right? Maybe the HR source system is very different from the finance system. And so to make sense of that data, we need to make it conform to some sort of data model. And then we have a service area, and often this is a self-service area, where we allow our business intelligence and data analysts to access that data in a really conformed way that can build reports, and this whole thing can be a single source of truth. Alternately, and maybe in the olden days, if we had the business intelligence and data analyst people access the source systems directly, then we have problems because we have extra load on the source systems, and we have source systems that have data in probably vastly different structures. So what we do is we build data engineering pipelines that ingest the data, transform and conform the data, and then we have a service sort of data fabric where our business intelligence folks can access that data and build reports, alerts, and dashboards that actually tell the truth. Finally, let's talk about architecting for DevOps. This is where the people part of a system comes in. So what is DevOps? It's kind of a buzzword that's out there, also sometimes known as SRE. They're a little bit different, but they're mostly the same. It's really software development practices moved over to IT operations. And we've seen that happen when we talked about infrastructure as code. We can now use software development practices to operate and run and build our IT infrastructure and architecture. DevOps is based on manufacturing philosophies and principles derived in the 20th century, like Lean, Theory of Constraints, Toyota Production System. You've probably heard of all of these being in a business school. Some big thinkers of the 20th century, like W. Edwards Deming and Eliyahu Goldratt, for example, brought us to where we are today in DevOps. DevOps enables the fast flow of planned work into production. And there are 4 types of work in DevOps. There's planned work, there's unplanned work, which is break fixes, there are IT projects, and there are business projects. 4 types of work in DevOps. DevOps enables rigorous testing and fast feedback. If we're building something that doesn't pass our tests, and our tests are often automated, we need to know immediately so we can address those failures or those issues. We want to build systems in DevOps that give us that automated fast feedback. And DevOps enables a culture of continual learning and experimentation based on the scientific method. That means we come up with a hypothesis of what could improve a system or fix a system, and we have a dev and test environment where we can try out our hypothesis and see if it actually works before we put it into production. DevOps is all about continuous integration and continuous deployment. So we want to build systems that have dev and test environments where we can continuously test our new hypotheses, continuously integrate them, and then deploy them to production once they pass our certain tests. DevOps enables small teams to work independently. Remember, systems are built in the modern world with isolated components. But remember also that people are part of any information system. These components, including people, are architecturally separate, but they communicate with each other. So they come together to form a whole system. Remember the 5 components of information system: hardware, software, data, processes, and people. People are the most important part. Okay, so how does the cloud actually enable DevOps? I told you what DevOps was. I told you the cloud enables it. But how? By automatically and rapidly deploying development and testing infrastructure and then remove it when we're done. That's one really good way that we can use the cloud, and specifically containers in the cloud, to build a DevOps environment. We can have software developers push a button on their whatever development tool they're using that runs infrastructure as code, that builds a dev and test environment that exactly replicates the production environment, but it's safe to test in. Have some automated tests and even some user tests and manual tests to test the software code or the feature that they're wanting to deploy before they deploy it. And only when it passed the test, then we deploy it to actual production. And then when we're not testing anything, we want to destroy that testing infrastructure so that we aren't paying for it. Remember that in the cloud, generally speaking, we are on a pay for what we use model. Works beautifully with containers, and we'll talk about containers in a future video. Thank you for joining me in this video, and I look forward to seeing you in the next one.